Hello everyone. In this demo presentation for the COMSNET 2023 demo and exhibit, I am going to present the demonstration for deep learning based BPSK demodulation via software defined radio. We are from ARC Lab in Indian Institute of Technology, Ropar, and this work has been done under the guidance of Dr. Satyam Agarwal. The overview of this presentation is we will see that how BPSK transmitter and receiver by a conventional method has been done and its challenges, a quick review of machine learning, then our proposed DNN based architecture, how we are going to train it, and then DNN based receiver structure, and we will see a quick video of the demonstration, and then finally we conclude this presentation. So just going to introduce how the transmitter, we have to know how what is BPSK. So BPSK use binary 1 and 0 to change the high frequency carrier signal and to change the phase of high frequency carrier signal. So for binary 1, let's say we have no phase change, and for binary 0 we have 180-degree phase shift. So the important part to learn here from is that for binary 1 we have some time period TB for over which our carrier signal has no phase shift, and for binary 0 and we have 180-degree phase shifted cosine signal over a time bit period TB. So let's move and see how our transmitters look like. So we are using a text signal hello world, which is converted into a binary signal using an ASCII code, and we form a basic packet by concatenating the binary signal with a preamble. We modulate this BPSK signal via we modulate this packet via BPSK modulation scheme, and it has been this baseband signal is converted into RF signal via SGR, which transmit the signal over the air. Let's see how the conventional receiver setup looks like. So the first block is again the USRP. So it converts the RF signal into the complex baseband signal, and this complex baseband signal is then used to process by the Simulink or any other suitable software. So this signal is passed through various blocks to remove the impairments such as offsets of frequency and time delay, then again phase offsets, and finally the conventional demodulator has been used to detect the correct binary output. There are several challenges in the conventional methods such as noise, path loss, fading, synchronization, and hardware imperfection exist. So in order to remove these effects, we are using various modules as we seen before, like symbol and carrier synchronizer, phase offset estimator, and its correction. So these are complex in nature, and in a large domain it costs. So in order to remove those, in order to learn, so the machine learning we are using learns the pattern of these impairments and such that it is able to detect the correct output with these impairments exist. So a quick review of machine learning is nothing but it learns the pattern and maps some relationship between input and the required output. So we are using a neural network which is trained via supervised learning to classify binary 1 and binary 0. So our current problem is a classification problem. Let's see the architecture of our proposed DNN. So it contains an input layer, 4 hidden layer, and 1 output layer. Input layer receives the k number of samples. So these k number of samples are nothing but oversampled data over a bit period. The hidden layer are the in number of 4, which contain numerous neurons and all use a ReLU activation function. The output layer is single neuron with sigmoid activation function to predict the binary output 1 and 0. This DNN is trained with sufficient amount of data and maps the input to the desired output with the existing imperfections. So let's see how this is going to be trained. So for every bit we have k number of samples and we concatenated it for n the number of bits. So we have a matrix of size k cross nb, and with respect to this we have another row vector which contain nothing but binary 1 and 0, which is used as a label for the supervised training, and it represents that these k samples represent the binary 1 and or 0. So let's quickly see how receiver structures look like. So again, we received the bandpass complex signal from the USRP at the receiving end, which convert RF signal to the IF signal. So we have assumed that bit boundaries are known. So we used a bit boundary detector separately, which feed the data, which feed boundaries to our frame detector and the data. So to visualize how this works or how it's look like, let's see what's happening. So over a bit period, we have 5 number of samples. So since we need these 5 samples to represent either 1 and 0, so with a bit boundary, we have first 5 samples. Again, for another boundary, we have next 5 samples. So for K, we have selected 5 samples over a 1 week period. Then these samples, which are in a form of row vector right now, so we reshaped all these row vector into a K cross NB matrix form via reshaping block. So the complete packet has been converted into this matrix, and the DNN is able to predict the output for a complete packet at once. So this is our DNN inside the Simlinks look like, which is fitted with the trained neural network and provide the binary output, which is converted back to the original text which was transmitted. So this is our experimental setup, how it's look like. So this is our setup inside the door, and another setup at the corridor of the building, and one more setup we will be looking at the outdoors. So let's see how it's works. So we know that again, yeah. So this is processing part. So we generate our packet here, and it's BPSK modulated. So this signal is still in the bandpass form. Then this signal is up converted and feed it to our SDR. This is the virtual block of SDR, and the physical form of SDR is connected to the Simulink. So this is B210 acting as a transmitter. So since we are using wireless transmission, we required amplifier to cover a large distance. This is our transmitting antenna, which is a log periodic antenna. Again, at a receiving end, we have another log periodic antenna, and this transmission has been done at frequency of 915 megahertz. At the receiving end, we have another SDR block B205 mini, which converts this RF signal or high frequency carrier signal back to the complex baseband signal for the processing by our DNN. So at the receiving end, we have the baseband signal, and which we will be processing. So let's see, let's start our transmitter. So we see that the transmission has been started, and so yeah, the transmission has been started, and the signal is received at the receiving end. Yeah, so we can see that signal is receiving here, and the signal strength is varying simultaneously with every packet. We can also visualize the spectrum of the received signal with its current strength, and the bit error rate has been calculated for every packet. So this is our number of bits. Since there is no error, and so our bit error rate is still 0. The signal strength is varying by changing the gain of the transmitting antenna. So for every 200 packet, we reduce the transmission gain by the factor of 1. So we can see here that currently the gain is 40 here, but with completing of 200 frame packets, the transmission gain is reduced by 1. So that's how inside the lab we check our setup. However, at the outdoor setup, we are going to look, we use distance as another parameter to reduce and varying the signal strength. So this is the transmission has been already started here. So at the receiving end, we can see that our bit error rate is 0, and we are collecting the signal. And again, as the signal strength is varying simultaneously, and at this point, our signal strength is nothing but in between 4 to 5 dB. So with this quick demonstration has been presented here, and with conclusion of this presentation is that the ML-based algorithm can easily be applied to the hardware and provide a substantial improvement in the performance. However, it required a large amount of training data and processing time. Processing time includes the training time as well. There are various applications of our proposed method in industrial IoTs, military communication, or wherever it's required high accuracy under very low SNR. The machine learning algorithms can also be used at the various level of wireless communication, such as channel estimation, encoding, and decoding. This is with this the presentation is concluded. However, this is a quick presentation. We will be there physically to demonstrate in more detail and show some exciting results. Thank you.